Now we are going to begin looking at mass wasting. Mass wasting. So what is mass wasting? Before we think about mass wasting, we should think about some key terminologies. And one is regolith. Regolith. All right. When we say regolith, it means loose, uncemented mixture of soil and rock particles. Regolith means loose, uncemented mixture of soil and rock particles that covers the earth's surface. Loose, uncemented mixture of soil and rock particles that covers the earth's surface. All right, so mass wasting is a downslope movement of regolith without the aid of water, ice, or wind. So the downslope movement of regolith by the force of gravity alone. The downslope movement of regolith. Mass wasting is the downslope movement of regolith by the force of gravity without the aid of a transporting medium such as water, ice, or wind. Does that mean water does not play a role? Not at all. Water plays a role, but the material is not being moved by water. It's not being transported by the water. It doesn't mean water may not facilitate this. So water will play a role, and very soon we'll see the actual role of water in mass wasting. All right. Now, since water, we are saying there's no transporting medium, in order for us to be able to have movement, then the material needs to be on a slope. All right, because regolith will only move if it is on a slope. Regolith will only move if it's on a slope. Right. So water plays a key role. It is part of a continuum of erosional processes between weathering and stream transport. All right, between weathering and stream transport. So don't forget, in order for regolith to move in a mass wasting process, it must be on a slope, since gravity will only cause motion if the material is on a slope. All right, gravity will only cause motion if the material is on a slope. All right. So we all know what gravity is. It's a force that acts everywhere on the Earth's surface, and it pulls everything in a direction toward the center of the Earth. So here we see a block on a slope, and that's gravity. How about sediment flows? So when we say sediment flows, it's a mixture of rock, regolith with some water. What is a sediment flow? It is a mixture of rock, regolith, and some water. Sediment flow is a mixture of rock, regolith with some water. And we can break down the sediment flows into two types. All right, we can break down sediment flows into two types. So these sediment flows occur when sufficient force is applied to rocks and regolith that they begin to flow downslope. So when they begin to move, rock, regolith, and some water, you see, it's not the water that's moving it. It's just that it has facilitated the movement, but the material is moving under the action of gravity down the slope. And we can classify this in two parts. All right. We have what you call granular flow and then slurry flow. We have granular flow and what? Slurry flow. What is slurry flow? Slurry flow means we have between 20% and 40% of water in the regolith or sediments, in the sediments. 20% to 40% of water, we call that slurry flow. If the water exceeds 40%, the slurry flow becomes a stream. All right. Then we have granular flow. Granular flow occurs when there is absolutely no water in the sediment or up to 20% water in the sediment. Is it possible to have movement or flow without water? Yes. We could have a case where air acts like a fluid and you can see sand flowing like a river, especially in arid regions. When we use the word arid, Arid means dry, desert, arid. So in granular flows can occur in desert or arid zones, desert or arid or dry areas, where water, little water could cause the motion, or we could have absolutely no water, but the sand particles will flow like a river. The sand particles will flow like a river, and that gives us granular flows. All right. So granular flows are possible with little or no water. And between 0 and 20% water, we have granular flow. And between 20 and 40% water, we have what we call slurry flows. Slurry flows. So typical examples of slurry flows, we have what we call solifluction. And the process of solifluction is the downslope movement of soil due to recurrent freezing and thawing. So that is more like in the case of the temperate zones. So that is solifluction. You could also have debris flow and mud flows. So these are typical examples of slurry flows. In fact, we can have debris flow also under granular, all right, under granular, all right. But precisely in the granular, we could have creep. Creep, just like the word creep. Creep means slow, gradual. Is that not it? Slow, gradual, creeping plants, creep. So slow and gradual movements, we could have creep, air flows, grain flows, and so on and so forth. But the most important thing I want you to know is that slurry flows involve higher amounts of water, 20 to 40%, whereas granular flows involve relatively low or no water, 0 to 20% water in the sediments. So that's the most important thing I want you to get, the difference between slurry flow and granular flow. All right, solifluction, that one involves the slow downslope movement of soil due to recurrent freezing and thawing of the ground. That is what we call the process of solifluction. Solifluction. So what are the factors contributing to mass wasting? So in order for regolith to move in a mass wasting process, we already stated that it must be on a slope, right? Because gravity will only cause motion of the material if the material is on a slope. Now, when the gravitational force acting on the slope exceeds its resisting force, slope failure occurs. So we have a slope, all right? We have a slope, and then we have the material on the slope. So if the force of gravity exceeds the resisting force here, then it means that the material will move downwards. And then we say failure has occurred. Failure means total loss of integrity in the material. That's failure. Failure in geotechnical engineering. Failure means the material, when we say a material has failed, it means that the material has basically lost integrity. It has collapsed. All right. And there are some two key parameters that govern this failure we are talking about. So the slope material strength comes from two parameters. One is cohesion, and the other one is friction. Cohesion is a binding force, and friction is a resistance force. Cohesion and friction. For instance, when you take clay particles, they easily bind together, so that is cohesion. When you take sand, loose sand, no cohesion, but the particle-to-particle resisting force, that is what the internal friction or the friction. Is that clear? So these two parameters, all right, provide a measure of the stability of the slope. So these are known as the shear strength parameters. Cohesion and friction are called shear strength parameters. So this specific strength we are talking about is called shear strength. If you remember from your basic mechanics, we have a box like this. This will be what? Tau. This horizontal forces is the shear stresses. And then over here, we have what? The normal stresses, or the normal force over area gives us the normal stresses. Typically, we use the symbol sigma. or stress. So normal stress and shear stress, horizontal shear stress. So this is normal stress and shear stress. So this shear strength, all right, meaning the resistance of the soil to shearing forces, is controlled by cohesion and friction, controlled by two parameters, cohesion and friction or internal friction. So the shear strength, which is the resistance to shearing stresses before failure, is controlled by two parameters, cohesion and friction. Now we can talk about what we call the angle of repose. The angle of repose. So the word repose means rest, like to rest. So the angle of repose is the steepest angle that a cohesionless slope can maintain without losing its stability. So when we say cohesionless, it means that like we are dealing with something like loose sand because there's no cohesion or binding force between the particles. Like when you take a heap of sand, there's a particular angle where it will not collapse. That is called the angle of rest or repose. When a slope possesses this angle, the shear strength perfectly counterbalances the force of gravity acting upon it. So no failure will occur. But if you go and cut it or you go and change this angle, you do something to it, then it will fail. It will fail. When we say unconsolidated, it means that the particles are not bound together. There's no binding between the two particles. So that is what we mean by the term unconsolidated, not binded together, unconsolidated. All right. So cohesionless means there's no cohesion. And for unconsolidated materials, typically we have them to be cohesionless. Cohesionless means there's no cohesion. Absolutely no cohesion. Even sand with some amount of clay will have some cohesion. Sand with some amount of clay in it will have cohesion. So cohesionless is like pure sand, like the one we use for construction. So we have occurrence of mass wasting processes. Mass wasting can be very slow or it can be very fast, right? So particularly in areas that are very dry or those areas that receive sufficient rainfall, we can have slow. Look at this deformation here, creep, right? Gradual movement here. Very slow rate. And it can be very fast, like this landslide burying villages. Or this, look at this huge boulder. Will you survive? Look at, there's a track here. There's a track right here. This huge boulder landed on the road, possibly triggered by some rainfall events, which caused it to roll down. Look at the size of the boulder. Just imagine the sheer size of the boulder. So it can be very fast or it can be very slow, depending on the conditions or the circumstances. It can be very fast or it can be very slow, depending on the conditions or circumstances. All right. You recall that we said that water does not really cause or is not an agent of mass wasting, right? Water, when we talk about mass wasting itself, water is not supposed to move the material, although it plays a role. So water can affect mass wasting in two ways. One, if the amount of water in the soil is small, it will rather help the soil particles to stick together. Like think about sand. If some little water will cause it to rather stick together, right? It will increase the cohesion. So small amounts of water can strengthen the soil and rather strengthen the soil. Too much water will increase the pressure between the grains, what we call pore pressure. And if the pore pressure increases, what happens? Friction will reduce because we need the particles to be in contact to have friction, right? So friction would reduce, and this would accelerate the erosion process and result in different types of mass wasting, all right? So too much of water may act to increase the pore pressure, which will reduce friction and then accelerate the erosion process. and this will result in different types of mass wasting. All right, this will result in different type of mass wasting. So little water is good. It strengthens the soil. Too much water, the soil will fail. That's the role of water, the importance of water in mass wasting. All right, that's the importance of water in mass wasting. So if in a short quiz, I ask you to discuss the importance of water in mass wasting, we expect that you tell us that when small amounts of water can strengthen the soil, because the surface tension of the water increases the cohesion, and a lot of water would increase the pore pressure, meaning friction will reduce, and then we are going to have an accelerated erosion. All right. Okay. We have different types of mass wasting events. For instance, here we have what we call a landslide. I'm sure you've heard the term landslide. The downslope movements of material, it can be bedrock, it can be regolith, it can be a mixture of this. We call that landslide. But the downslope movement of regolith itself, with the action of only gravity, is what we call mass wasting. But when we say landslide, it means that there's a downslope movement of material. All right. It can be regolith or a mixture of this. So we can classify this into two main parts. The first is what we call slope failures. So a sudden failure of the slope. All right. And the second one is the one we dealt with, sediment flows. Material is flowing downhill, mixed with water or air. And we divided the sediment flows into two, granular flows and what? Slurry flows, right? Depending on the amount of water. So here we see different types of failures, and we can broadly classify all this as mass wasting processes. We have a rock fall, we have debris flow. This is what we mean by debris flow. We have a slumping, we can have creep, gradual deformation, rock slide, debris slide, or these huge chunks of blocks could also collapse. And we classify that, so we call that block slide. And we could equally have subaqueous sand flow. So involving some kind of water, subaqueous sand flow. All right. So the last thing we want to talk about now is the triggering events of mass wasting. Mass wasting can be triggered by three things: shocks, slope modification, and undercutting. All right. What is a shock? A shock can be vibrations, blasting, heavy vehicular movements, earthquakes. All these are shocks, and they can cause mass wasting. Another thing is slope modification. So we talk about the angle of repose, which is the steepest angle at which a cohesionless material will stand without failing. And for cohesionless material or loose materials, it's typically between 30 to 37 degrees, right? With respect to the horizontal. So if I have a slope, all right, and that slope, we end up cutting the slope badly, like this. We modify the slope. The material here will not be stable again because we change the angle of repose. So it will collapse. It will collapse. Every material here will collapse. And that is what we call slope modification. All right, it will collapse and the slope will get restored again. Rivers and streams can also undercut the river bank. They will undercut it. Can you see? The river or the sea or the stream is eating beneath, removing material beneath the cliff, and ultimately this will collapse. This side will collapse. So that is undercutting. That is undercutting. So these are the type of triggering events that could cause mass wasting. That could cause mass wasting. All right, so this brings us to the end of the topic mass wasting. Mass wasting.